Hello, ladies and gentlemen. Welcome to our Honors Chemistry Acids and Bases Lesson 2. So we are working on 14.2. Just a heads up, you will be getting a worksheet for every one of these lessons. So you got a worksheet for 14.1. Today will be 14.2, and then next week we get 14.3 and 14.4. So don't let those pile up. See if you can get those done within each lesson day that I assign them. All right, next week on the Monday, Tuesday lesson, we will also have a brain training that's going to focus on the 14.1, 14.2 worksheets. Ask me in an email any questions that you have on that, and we will go from there. All right, so today we're working on the strengths of acids and bases. We have weak acids and strong acids. And we're also going to learn something called autoionization. So you will need your periodic table and the specific different boxes I showed you last lesson, and then also your calculator, because we're going to do some problems. Oops. There we go. All right, so quick review. We are going to look at this problem. What are the conjugate bases of the following acids? So when we have an acid in a reaction, imagine you've got that first one, H2CrO4, and it's on the reactant side of a reaction, and you've got a base with it. Doesn't really matter at this point what the base is. The acid, by definition of our Bronsted-Lowry acid definition, the acids are going to donate a hydrogen ion, your proton. So let's take our H2CrO4. Now imagine it gives up an acid. What would it look like? Well, it would have only one hydrogen left. Imagine it gives up a hydrogen. It's only going to have one hydrogen left and a negative ion, or a negative charge, because your hydrogen is an ion in this case. So there's your base, conjugate base. Here's your acid, and here's your conjugate base pair. So for the next one, we have HNO3. Losing a hydrogen is going to look like this, NO3 minus. The charge is very important, don't forget that. So then the next one, HSO3, it already has a minus charge. So when you lose a hydrogen ion, it now has a 2 negative charge. All right, so let's go ahead here. I'll make this larger if possible so you can see those for a second there. All right, so let's go on to our next one. Whoops, I went too many. So we're going to look at our strengths of acids. If you look on your periodic table here, we have in this box right up here, we have our strong acids, and you can see there's a list of 7 of them. Strong acids completely dissociate in water. So think of your ionic compounds. Do you remember in an earlier unit we talked about how ionic compounds completely dissociate in water? That means they completely separated. They were no longer existing as a compound bound together, but they were existing as separate ions. Well, that's what acids, strong acids, do. Interesting thing about acids is they're actually covalently bonded. They're not ionic. They are sharing electrons. They didn't transfer an electron between the hydrogen and your anion, but they also completely dissociate, which is really interesting. So you have a covalent bond completely dissociating. So your strong acid, we have an example of HA. Of course, your H is your hydrogen. Your A is representing the negative component of your acid. And if you mix a strong acid with water, you have a 1 arrow pointing that direction, which means this is a completion reaction. In strong acids, because they completely dissociate, all of the reactants are going to turn into the products. Here's your acid. By definition, it's going to give up a hydrogen to the water. So then you have A minus plus then the H3O, which is your water with the extra hydrogen. So there you have it. Whatever concentration you have of your strong acid, you're going to have that same concentration of H3O. If you remember that concentration is often used, let's put an A in there. Here's your general strong acid. HA in the brackets, that means the concentration of that. So concentration is in units of molarity, usually. So your HA, concentration of HA, is equal to concentration of H3O, and that's simply because of your stoichiometry. If you notice, we've got a 1 to 1 to 1 to 1 ratio here. So however much HA you have, or strong acid, you also have that same number of H3O. And it says that on your strong acid box. It says strong acid in brackets is equal to H3O in brackets. We're going to get to that in the next lesson. So there's that. Now the difference between a strong acid and a weak acid is that a strong acid doesn't dissociate completely. It only dissociates partially. So now if your HA represents a weak acid and you mix it with water, the only difference is that we have a double arrow now, which if you remember from our last lesson, that means that some of the reactants turn into products, but then some of those products turn back into reactants. So we're moving back and forth. This is your equilibrium reaction. And it has the same products that we had before. A minus plus H3O. I will make this a little larger. Maybe we can see that better. So your HA, even though we still have a 1 to 1 to 1 ratio here, your concentration of the weak acid does not equal concentration of H3O because some of that H3O turned back into HA. So we don't know how much of it actually dissociated because only partially did. So when we learn about our weak acids in a future lesson, we'll come back to this and figure out exactly how much turned into H3O. These are what is called reactant-favored reactions, which means when you have in your beaker, imagine, you pour in some weak acid with your water, and then some of those turn into the product. So you have all 4 of these species in your beaker. It's a reactant-favored reaction, which most of the species you have are actually reactants, not products, which is a different concept than what we've talked about so far with our completion reactions. So let's move on to our next slide. These are the strong acids. We have 7 strong acids, and you're going to have to memorize them. Wink, wink, you don't, because they're listed right here on your periodic table. Those of you who are going to be taking AP chemistry with me next year, yes, you will actually have to memorize them, but don't worry about that. There's a very easy way to memorize them. We'll figure that out next year. Don't worry about it. All right. So there you have it. You have a couple of binary acids, HCl, HBr, HI, and then you have HNO3, HClO3, HClO4, and then you have one diprotic acid. Diprotic meaning 2 protons. Well, if you remember, our hydrogens in acids are technically just protons because they have lost their electrons. So that H2SO4 is your diprotic. It has 2 hydrogens in there. All right, so there's your strengths of acids, your strong acids. We're going to move on to the autoionization of water, and we'll get back to strong and weak acids later in next unit. But for now, we're going to work on our autoionization. All right, so as we've seen in our last lesson, that water can act as both an acid and a base. It can donate a hydrogen as well as accept a hydrogen, and that is what is meant by amphiprotic. It can do both things. Think of what an amphibian is. Amphiprotic, it can do 2 things with the proton. The protic is where that comes from. So in pure water, you have H2O plus H2O, of course, in pure water. A few of those molecules, very few of them, can act as an acid, and very few of them will act as a base, which means that some of those water molecules will give up a hydrogen to other water molecules, and then you would come up with your reaction here, your H3O and your OH as products. So if we write that out up here, we have H2O liquid plus H2O. We have our double arrow here because not all of your water molecules are going to turn into your products. So you have your hydronium, which is your H3O, and your hydroxide, your OH. So one of these water molecules gave up the hydrogen to the other one, making it look like this. Now when you have a glass of water, a teeny tiny minuscule fraction of those molecules look like this. The majority of them look like this here, actual H2O molecules. So that is what is autoionization. All right, we're going to get back to that in a second, but first I'm going to show you or explain what an equilibrium expression is. The equilibrium expression is the concentration of your products divided by the concentration of your reactants. And it's very important, only aqueous solutions or aqueous species are involved in here. So if you have liquids, solids, or gases, you completely eliminate them and you don't have an equilibrium expression for them. It's only for aqueous. So if you imagine you've got a reactant, you've got reactant plus reactant turns into product plus product. You have your product concentrations multiplied together divided by your reactant concentrations multiplied together. And of course, when you have your brackets, that means the concentration of whatever is in the brackets. So let's go to the next slide. Back to our water molecule reaction. You notice these two are liquids. They're not aqueous. Only these two are aqueous. So if we have products divided by reactants, we can only take our products. We have no reactants in the bottom of the division because, well, they're liquids. They're not aqueous. So then our Kc, which is what equilibrium expression variable looks like, we only have our products. The concentration of H3O times the concentration of hydroxide. You can't say divided by reactants because these are just liquids. Your equilibrium expression for water is special. It gets its own little variable. Oops. And we have Kw, where W, of course, stands for water. So at 25 degrees Celsius, this Kw is always equal to 1 times 10 to the negative 14. And memorize it. Wink, wink. Don't memorize it. It's on here. In our, what am I looking at? Acids and bases. Nope, it's not there. Where is it? Uh-oh. Well, we'll get to that in a second. I'm not seeing it on here. Go ahead and write it in then. We need Kw is equal to 1 times 10 to the negative 14. If you see it, let me know, but I'm not seeing it right now. Okay, so maybe you do need to memorize it. Haha. I'll give you 2 for a quiz. Well, all of our tests and quizzes are open book anyway, so don't worry about it. 1 times 10 to the negative 14. Very important number. Let's move on here. Here is a sample question. Let's pull this up so you can see my work on. Oops. There we go. Okay. So here's a sample problem, and it's actually the concentration of hydroxide in solution is found to be this, 1.4 times 10 to the negative 11 molarity at 25 degrees Celsius. What is the concentration of H3O? Okay. So we have this equation right here. These two multiplied together is equal to 1.0 times 10 to the negative 14. We're being told that our hydroxide concentration is this, 1.4 times 10 to the negative 11. What's the concentration of H3O? So if we have hydroxide, let's divide both sides by hydroxide, and we can solve for hydronium, which is the H3O. Divide both sides by hydroxide, and we get that down here. That's going to equal H3O. Of course, hydroxide is equal to this from the problem, so we can plug that in, and we've got 1.4 times 10 to the negative 11. All we have to do is plug this into our calculator. Now, if you remember anything from the last year of chemistry, when we have an exponent in the denominator, you have to put parentheses around it, otherwise your calculator is going to mess up. It's not going to interpret what you want correctly. So we're going to type in 1 times 10 to the negative 14 divided by parentheses 1.4 times 10 to the negative 11. Close the parentheses, press enter, and you should get 7.14 times 10 to the negative 4. If you don't get that, you probably forgot your parentheses. So go ahead and double check that really quick. All right, let's move on to the next problem. Okay, so autoionization example 2. Write the dissociation reaction for HCl in water. All right, so we have HCl, hydrochloric acid. It is one of our strong acids. We know it's strong because it's on our strong acid list. If anything is not on that strong acid list, then it's a weak acid. So it's very easy there. HCl, we want it to dissociate in water, so then our other reactant is H2O. We have a single completion arrow pointing to the products because we know it's a strong acid. It's going to completely dissociate. All of the reactants will turn into all of the products. Your hydrogen from your acid is going to be transferred to your base. So then we have Cl minus plus H3O plus. There's your dissociation reaction for HCl dissolved in water. It's balanced. You have a 1-to-1 coefficient ratio there. All right, so then it says if 2 moles of HCl is dissolved in 1.5 liters of water, what is the concentration of the H3O and OH in the solution? All right, so concentration is molarity, moles over liters. So we've got 2 moles, and we have 1.5 liters of solution. Take your calculator. 2 divided by 1.5, and we have 1.33. 1.333. There's lots of 3's in that number. There's your molarity of HCl, your strong acid. Because all of the strong acid dissociated and we have a 1-to-1 ratio, this is also equal to the concentration of H3O. So that answers half of our question. Then it says to find the concentration of OH. Well, we know that our 1.0 times 10 to the negative 14 divided by H3O is equal to OH. And that is from this, our equilibrium concentration, or equilibrium expression for water. That is where you get here. Just rearrange it. H3O from the problem is equal to 1.333. Keep in a couple extra digits for sig figs. Let's try that. We've got 1 times 10 to the negative 14 divided by 1.333, and we have 7.5. Let's see, how many sig figs do we need? 1, 2, it looks like. 7.5 times 10 to the negative 15. 15. And there's your hydroxide concentration. This technically should be rounded to just 2 significant figures, 1.3. All right, so there's that problem. Moving on. So for all of the 4.2 problems on the practice problem list, you need to remember these things. Kw is equal to H3O times OH, and that's equal to 1 times 10 to the negative 14. For some reason, I'm not seeing it. Oh, no, never mind. It's right there. Right in front of my face. It's on here. So it's on your periodic table. H3O means hydronium. That is actually listed on your common polyatomic ion list at the very bottom where it says positive ions. You have ammonium and hydronium, H3O+. So if a problem asks for find the hydrogen ion concentration or find the hydronium ion concentration, both of those mean H3O+. Your hydroxide is OH. So if a problem says find the hydroxide concentration, that means you're finding OH. And all of that can be found with algebra using your Kw equation. All right, so let's move on to problem 1 of our worksheet. I will do this for you and also the second problem to get you started. All right, so let's erase this. If you want, I would suggest you pause the video, see if you can work this out, and then make sure you have the correct answer. It's good to force your brain to struggle a little bit through this. You will be well on your way to succeeding. All right, so what is the hydroxide ion concentration with a hydronium concentration of 6.8 times 10 to the negative 10? Well, first, let's write out what we're given. It says you have a hydronium concentration of this. Well, what's hydronium again? That's your H3O concentration. And that's equal to 6.8 times 10 to the negative 10, 6.80 for sig figs there. We have three significant figures. Moles over liters, of course, means molarity. And it's asking what is the hydroxide? So it's asking for your OH. What is that one? Well, thankfully, we have a wonderful equation that says H3O times OH is equal to 1 times 10 to the negative 14. We're going to rearrange this since we have H3O to divide both sides by H3O. So we have 1.0 times 10 to the negative 14 divided by H3O, which is technically this number in this problem, 6.8 times 10 to the negative 10. Plug that into your calculator. Remember your parentheses. Let's go and write them in fact. So we don't forget. 1 times 10 to the negative 14 divided by parentheses 6.8 times 10 to the negative 10. Close your parentheses, and we have 1.47 times 10 to the negative 5. Molarity for, that's your hydroxide concentration. That's the end answer for this problem. All right, next problem. So here's problem 2. What is the H3O in a solution with OH of 5.67 times 10 to the negative 3? Identical problem, it's just switching. You're going to have the hydroxide concentration to start out with and ask for H3O. So it's telling us OH concentration is equal to 5.67 times 10 to the negative 3. Moles over liters is molarity, and we're asked for H3O. So we're going to take our 1 times 10 to the negative 14 divided by your hydroxide is going to equal your hydronium, your H3O. Remember your parentheses in the denominator. Let's try this. 1 times 10 to the negative 14 divided by parentheses 5.67 times 10 to the negative 3. And we have 1.76 times 10 to the negative 12. And there's your answer for problem 2 on the worksheet. There are only 9 total problems on this worksheet, so you should be able to do all of them based off these 2 examples. And I would suggest you work on the problems first and then check your answers. Don't just look at my answer key. Again, force your brain to struggle through it, and that is how your brain can grow. All right, good job. Thank you.